Hello, friends. It's time for some debriefing. On the last three videos, I showed you three, if you want, technologies to analyze a complexity, and I would like to sum up and find some common conclusion. But just to remind you, we had the option of a WordDistance. We programmed this in Python and had some graph theory, some classical graph theory without the embedding of a graph. Then we had the option word2vec. We did this in a TensorFlow 2 environment. And the third option we encoded was a sentence transformer methodology based on BERT transformers. We embedded sentences and detected the thematic clusters. And I think it is interesting to see the strength and the weaknesses of each of those three methods. Short summarization, the first method, the WordDistance, is simply calculated in 2 dimensions. You have one sentence, and in this sentence you have, let's say, 10 words. And you say for each word, okay, which other word is in this sentence given a target word, and the words from, let's say, 1 to 9 in this sentence. If you want to be a little bit more advanced, you count the distance of words between two words that you can say, okay, it's closer or a little bit further apart, but I did not find that this makes a significant difference. And if you have, I don't know, 100,000 sentences, you have words that are in, let's say, 100 of those sentences. And if you fold those 100 sentences, you get a very nice three-dimensional visualization. I showed you how to do this, and I showed you the visualization. And I will go over this in a second, too. The second methodology was word2vec. Word2vec, we had a TensorFlow implementation, of course, with Python 3, and we calculated here in 128 dimensions the semantic vicinity with a cosine similarity function, the semantic epsilon environment, let's call it in the mathematical term, of a certain word. Now, what is nice here, in the second option, we have words that are not really in the sentence because it is a kind of a semantic encoding. We have a shallow neural network. We take the weights of the hidden layer. We regard this as a tensor field, and we take it like a coordinate system. And in this topological space, we construct, from simplicities, we construct a space where we can have a cosine similarity function. So we increase the complexity, but gain some semantic context. And you will find here words that are semantic close, and maybe words that have not been in option number 1 in the first methodology, where there's a sentence where we had a target word like water or city. But here we have words that have not been in this particular sentence with the city. So here we advance our insight, our knowledge body here, and we find semantic similarities based on a higher dimensional interlink. Now, the third option was sentence transformer SBERT. We took one sentence. We said, okay, all the words in the sentence, we make a word embedding. We made some padding, yeah. We made some pooling layer. We showed you how to configure different pooling layers. We took a BERT pre-trained model. We performed some unsupervised learning given the datasets of several thousand sentences. We improved our model, and we calculated a dimensionality representation of each and every sentence. Then we applied some dimensionality reduction and a cluster algorithm. Within this cluster, we applied simply that we said we want to have a look at the words, at the bigrams, and at the trigrams, which have a very high representative degree and frequency within the set of words and the set of sentences. Of course, you can advance it even a step further and do some paragraph transformer encoding. Normally you have a sentence, let's say you have 8 to 10 words in this sentence, and you have a paragraph, and for simplicity's sake, let's say you have 8 to 10 sentences in a transformer encoding. Now, here, a complexity that you try to encode for one tensor representation, I don't know if you do not lose too much information in this particular paragraph transformer encoding, because suddenly you have up to 200 words. For each word, you do a word encoding, and then you make a pooling. You have a pooling layer over 200 words. Well, I did not find any result I would regard as satisfying, but hey, maybe you found a cool solution, or maybe there's a trick I did not discover. So it's definitely worth thinking about this methodology also. But let's have a look at the strength of all these three methodologies. Now that we have done all three, we encoded all three. Let's start again with number one, with the WordDistance or the graph theory, the classical theory. The frequency of bigrams in a sentence was the first step we did. Then we had a source and a target node for a graph representation. We calculated the weights of the edges. And then we came up after some folding where we had a node urban and a node city. And we had a look, hey, if I have both nodes, what is the interconnect? What are the nodes that are connected? Also with city and urban, what is here the set that I'm interested in? Which nodes are not connected to city, but only to urban, and so on. And we try to get some understanding in a simpler WordDistance presentation, which I would not call a semantic presentation, but a simple WordDistance. Of course, you could increase now the number of edges that you want to display. If you have a vocabulary size of, I don't know, 50,000 words, you can imagine that very easily you end up with millions of edges, multiple edges to multiple words, a complex structure. So here the art more or less is to find a low-dimensional representation where you get the data you're interested in. Data, smart city. So you see, we want to know more. We want to know now, for example, about data. What is the environment on data? What are the words that are around data? What about smart city? How are they interconnected? And the result, very easily, was delivered by a word-to-vec, a classical old-fashioned word-to-vec algorithm, a presentation in 128 dimension done by TensorFlow 2 calculation. And here we have exactly what I told you. We have urban, we have city, we have transport, pollution, air, water, all these major nodes, and how are they interconnected? And the dataset we have here are simple sentences of 34,000 R&D projects within the European Union that have been paid for by the European Union, the European Commission, within the H2020 program. So you can see here what are the interconnects between some nodes that you have chosen, you're interested in, and you want to see, hey, energy and transport, city with urban, what are the interconnects? What R&D is going on? What are the top 10 words in this regard? Of course, you can have a look not of the top 10, but of the least, of the weakest signal. You say, hey, the least top 10 from the bottom up, what are the weakest signals right now that nobody is investigating in, nobody is doing some research on? You can also have this presentation, and it is fascinating. I also start to look at the weak signals, and you see where some R&D starts to take off. And it's interesting to invest maybe in those areas if you're an investment company. And the third topic, of course, is sentence transformers. We have some word embedding, we aggregate it to a sentence embedding. And what we found here is now each dot is a sentence, as you can see. And the color-coded belong to a thematic cluster. And those gray sentences have not been assigned by our artificial intelligence system belonging to a thematic cluster. But this depends on the computer resources you have and the money you want to invest in a run under unsupervised learning. It is here, as I've showed you in the last video, done on a free COLAB version from Google. And what we get, and I guess we can get rid of the noise, is then a presentation where you have clusters. And you can switch on and off the clusters, and let me find the cluster here. Yes, exactly here. This cluster here is urban waste, wastewater, wastewater treatment, bio-waste, solid waste. And if you're interested in this, you can switch it on and off in this representation. You can investigate it further. You can say, hey, now I take only as a data set those, I don't know, 100 or 200 sentences, and I perform a cluster analysis on those clusters too. So you get a subcluster analysis that goes further in the topic of waste, wastewater, solid waste, bio-waste, metabolism of waste. And it is fascinating how you can go with a cluster algorithm based on a sentence transformer algorithm in the details. And don't forget, this is the summary of 34,000 R&D projects. I had not the time to read, but for my AI system, no problem at all. You can have here interlinks that are a little bit cross-sector, multidisciplinary, and we find out that depending on the fine-tuning of the parameter of the cluster algorithm, you can get a very nice understanding what are the major building blocks, what are major chunks of R&D that's going on in Europe in a particular area. And if you want to fine-tune it, you define, I don't know, security as one of your topics, you focus on security, and then you dive deep into all the security aspects. And if you widen the scope from a sentence embedding to a paragraph embedding to get the neighboring sentences, if the topic is about security in a particular paragraph, in a document, in a publication, in a PDF, on a web page, whatever, you will get the whole content and the environment of this content for analysis. So this is it. 3 methodologies. Each methodology can be built up on the other one. I showed you when we went through the 3 videos that the output of the first method was the input to my second method. I could refine my search, I could refine my query parameters to really focus on what I need. And I think it's a very nice application where you start simple, you end complex, but the insight that you get into this complexity can be fascinating. This is it for this video. I hope I see you in the next one.